All right, so today I want to talk about a visual programming paradigm called Bolt. Let me share a screen here. So Bolt is a programming API obtained by Unity from a developer Liquid. It's available on the Asset Store. It's not yet a package. It's kind of brand new, so it hasn't been made into a package yet. But and you can read all about it on this post. Here's an example of what one of these things looks like. Documentation that comes with it is has kind of a walkthrough of all the different details. And they describe two different types of graphs, a flow machine and a state machine. A flow machine or flow graph is one where we have individual actions and values, and they're executed in a particular order, just like a program. Whereas state graphs are very similar to what we've done with Mechanim. We have states and transitions among the states, where each state is essentially a flow graph acting as a program. So here's an example from one of the samples of a patrolling, chasing, attacking AI. They're the different states, patrol, chase, and attack, with the transitions among them, similar to Mechanim. And if I click on the chase here, it opens up the flow graph that is the chase program. It has an update function and a nav mesh set destination, and it's getting the player position to assign as the target. So a very simple, straightforward kind of thing. These modules are called units in the parlance of Bolt, and the little slots that you can connect via the various lines are called ports. And the flow follows those green arrows from one unit to another. There are lots of units, basically the entire Unity API, some 23,000 units. And you can find them by context or searching in their provided fuzzy finder. It works pretty well. While I've not tried it, apparently you can create your own custom units from C# scripts. In the setup process that you do at the beginning of Bolt, you can choose two different naming schemes, human naming or programmer naming. With human naming, you see something like transform : get position. With programmer naming, you see something more like what we're familiar to from the C# programming, transform.position get, integer versus int, that kind of thing. All flow machines have one or the other of start or update units. Start is executed once when the object comes into being, like the C# start function. And update is executed once every frame, also like the C# update function. There's also a late update and a fixed update analog to the C# functions. So here's a simple example. This is the Bolt version of Hello World. We have the start event, and here you can see the flow proceeding with these green arrows from the start event to the string clone that creates a string. There's nothing coming into the port here, so we put what we want the string to be in the provided box. The flow then goes on to the debug log unit, which takes as input the string message that's displayed on the screen. And that's all there is to this. So here it is. I've got my debug cube. That has a flow machine on it with the debug flow macro. That's the one that's showing right here. And when I run this thing, in the console, I'm going to see hello world printed in the console. So all quite simple. So to add one of these flow graphs, we need to add a flow machine component, which we get from the bolt menu. We add this to the object. It's a component. We then have we can assign it a name. I've assigned it to debug testing. There's an optional description, displays hello world. And then we drop the flow macro that we want in this slot. Here that is over here in Unity. So let's go on, and in this case, we're going to make the object rotate. We have an update that triggers every frame, and the flow goes on to the transform rotate. This is just like the transform rotate function that we've got. It has the object that we're going to rotate, in this case self, and then we have the X, Y, and Z Euler angles that we're going to rotate by, and the world space that we're rotating relative to. We have a get variable that the get variable is kind of the equivalent of an exposed variable, a public variable in a C# script. In this case, we're looking for an object variable that's on the game object self. There are several different variable types. The object variables belong to the game object. They're shared across all graphs on that game object, but there are also flow variables that are equivalent to locals. They're graph variables that are local to the particular flow graph, and they're scene, application, and saved variables that are accessible as well. The variables are included as a component, a bolt component, the variable component. And here we get to add variables with an assigned name. So here's rotation rate. We specify its type and its value. And again, this is just like an exposed variable in a script. These are accessible from the graphs. So let me get in the rotate scene. So here's my cube. Here are my variables, rotation rate, color I'm not using, but it's there in case I wanted to. And here's the flow machine component that accesses the rotate flow macro, which is the one that's showing in here. One thing that's kind of useful is we can hit the, we can go into full screen and overview, and this then zooms it into its as far as it can go. And let me get this up down here. And back out of full screen, and overview should fill the objects so that they fit in the screen. So the other part of this, I have the update going to the transform rotation, but something is feeding the X, Y, and Z Euler angles because nothing's going into X, it just gets the default value 0. But the Y and Z angles are coming from the exposed variable rotation rate. We're passing this through a per second module. Per second is kind of like multiplying rotation rate by time.delta time in C#. And so this is giving us a number of events at a particular rate, a number of events per second. I'm passing one version of this straight to the y angle, but another version of this I'm passing into this multiply operator or unit, and the multiplier operator takes two inputs, A and B, and it multiplies them and provides them as the output that go into the Z angle. Since there's nothing coming into the B port, I'm able to specify a scalar value here of 0.5. So this is going to rotate, it's going to take the rotation rate, which I believe is set to be 100, and it's going to rotate the y angle at 100 degrees per second and the Z at 50 degrees per second. So let's run this and see if it actually happens. This is another interesting feature. There's a setting where you can turn on the flow so that you can actually see it happening. And as it happens, you get to see the different values as they pass through the flow here. These are basically the frames, I would guess, and then these are the different values that are feeding this. This automatically knows to go back through this chain and draw these values in. So one other tool here is the graph inspector window. And so with the graph inspector window, if you select one of the units and you have the graph inspector window showing, which I do over here, it kind of gives you a documentation for that particular unit. So for instance, the get variable gets the value of the variable. It has an optional fallback if it's not connected, what kind it is, that's flow, object, scene, graph, save. And it describes the inputs, a string, and the object that the variable lives on, and the output is the value that of the variable input. So this lets us kind of see what each of these different modules do. Returns the frame rate normalized value of a scalar, multiply returns the product of two scalars, rotate implementation applies a rotation Z, X, and Y about those axes, exactly like the transform rotate function does. So I kind of implemented a variation on the brick shooter that we did back in 3.12. First, I wanted to make a tool that moved my gun tip around. I'm going to emanate bullets from a gun tip. A gun mover C# script might look something like this. We have an exposed variable speed. And in the update function, we catch in the V and H the vertical and horizontal axes scaled by speed. And then I create a vector move that is time.delta time times that vector with the H, V, and 0 in it. It's going to move my gun tip left and right, up and down. And I add that to the transform position to move things. With a flow graph, I have again an object variable. This is going to get that gun move speed. I have two get axes here that are part of the flow of things along the horizontal. I have a time.delta time that I multiply that gun move speed by. and I pass it on to the output of the two axes. Here's the output of the uh, horizontal axis. Here's the output of the vertical axis. And so this multiplied value goes into the B slot of both these multiplies. Then I create a vector. The output here goes into the X component of the vector. The output of the vertical axis goes into the Y slot of that vector that I'm creating. I get the position of my object, and I add this vector to the position of the object, and I pass that on to the set position of my transform. So let me show you that move. So here's my gun tip. Uh, my gun tip has in its inspector, it has a flow machine gun move flow micro, and it has various variables exposed. I'm only going to be using the gun move speed here, but I've also got a bullet speed for later when we start to fire bullets from my gun. So I'll play this. And let me get an overview here so that I can see the whole thing. So horizontal arrows move it left and right, up and down arrow, move it up and down. And if you look closely in these little flow things, you can see the different values of the horizontal and vertical axes. There's the horizontal axis. There it's at 1, there it's at -1. So you can see all of this going on in the flow graph. So I want to fire a bullet with the gun. So again, working through this in C#, it's pretty simple. We have an exposed variable for the bullet game object. We have an exposed float for the speed. And in the update function, if I press the jump button, the space bar, it instantiates a bullet at the transform's position. It gets the rigid body off the bullet component, and it adds force in the speed transform forward direction, and this fires the bullet. So doing this with Bolt, we again have the update that goes to the get button down, looking for the jump button. This goes to a branch. On true, it does something. On false, it does nothing. On true, it instantiates an object and adds a force to that object. The object is a get variable bullet that we pass here on to the object that we're going to the instantiate function. We get the position that of the gun tip, which we pass on to the position here, and we get the rotation of the gun tip, which we pass on here, so that our instantiated object has the bullet prefab with the transform's position and rotation. The bullet speed is another get variable. This one we pass into the multiply, here I'm going to multiply this by the transform forward, get forward. So this is the gun tip's forward direction. And the multiply is smart enough to recognize that this scalar times this vector gives me a scaled vector that I can then apply to the force. And there's also the optional force mode here. So that's that's a bullet. Where's the bullet? So here's the gun tip bolt with our gun flow on it, with our bullet speed, a value of 1,000. The bullet here is an empty bullet. It's just a rigid body. We'll do something with that later. And the gun move speed that I used before, a value of 5. So again, watching this one, I'm able to move this around. But when I press the jump button, the space bar, it triggers all that flow. Everything here is going into the false because I haven't pressed the button, so it's not doing anything. But when I press the jump button, now the flow goes through the true, and all of this stuff is picked up and fed into the different components here, and it fires a bullet that is hitting my wall there and knocking things down. It's not a very heavy bullet, so I have to really fire it. So cool. The next step is a script I'm going to put on the bullet, with the bullet, the empty bullet that just was a rigid body, it just kind of knocks things around. But I'm going to have it make a particle effect, and I'm going to have it destroy the properly tagged object that it hits. And so again, a C# script that will do this. We have the exposed variable game object, the poofer, the particle effect that we're going to instantiate. And in the on collision enter, I'm going to compare the thing that's collided with it, compare its tag and see if it's a block. If it is a block, I'm going to instantiate the particle effect at appropriate transform position and rotation. I'm going to destroy that 5 seconds later, so my poofer is cleaned up in the world. And I'm also going to destroy the game object that I collided with. So the flow graph for this starts with an on collider enter. And the flow goes through a compare tag with a branch, true or false, onto an instantiate the poofer, and destroy that after I guess 1 second, and destroy the object that I've hit, and destroy it itself. Things that feed in here, from the collider of the on collision enter, I feed that to the compare tag. I also feed it to the game object, get game object from the collider, and to the get position and get rotation, all of which I need for this instantiate. I'm going to pass the game object that collided with it to this destroy object, and I'm going to pass the poofer, which notice I haven't bothered with a variable here. This is kind of hardwired into the code so that I don't actually have to do it. I just drop the prefab into this slot, and it's hardwired. The self here is the object that the script is on, and the last thing it does here is destroy that as well. So with this version, the gun bolt version, we now have we have these two flow machines, the mover and the gun flow. This time the bullet is a different prefab. This time the bullet is one that itself has a flow machine on it. The bullet flow macro that I just discussed, here it is in the inspector. And so in this case, when I run this, unfortunately, I can't watch the bullets flow graph because it's not in the scene yet. But when I fire the bullet now, it destroys the cube that it hit. All those cubes are tagged to be blocks, and it instantiates that simple little poofer effect that just throws some sparks around. So cool. Now, you can imagine these are pretty simple. You can imagine that as programs got more complicated, that there'd be a lot more wires and graphs going around. Uh, and Bolt has this capability to encapsulate procedures into kind of user-defined functions. And I'll demonstrate that with a color changing flow machine, one that changes color of our cube. Let me show that to you first before we talk about it. So let me just run this so that you can see it happen. So basically I have a cube here. I have a cube here whose different color components shown in the UI elements are changing. They're changing at different rates. And you can see this fairly complicated graph necessary to implement this. But first, let's look at it in C# because it's instructive. This is the color changer script. It has public material and color speed. I'm using a vector for the color speed so that the red, green, and blue channels can change at different speeds that'll use that vector. I have privates for the renderer and my color, as well as for the 3 different sliders that I'm showing. In start, I'm going to find the sliders by name, extract their components, the slider components, and I'll get the renderer off the cube object, assign it its material to be the material that I'm, the exposed material, and assign and catch a copy of its color. Update is pretty simple. We going to vary the RG and B channels of my color with a little cosine function that adds 1 to the cosine function. So it's going to go, instead of going from plus or minus 1, it's going to go from 0 to 2. And then I'm going to divide it by 2. So it again goes from 0 to 1, but now all positive. And I'm using time.time to advance my cosine with X, Y, and Z components of that color speed vector. And then I just assign that color to my material, and I update the value of the 3 sliders. So well and good, but believe it or not, here's what it takes to implement that. This is that this graph that I showed you over here that I can't even make fit in the whole box. And the thing that we recognize here is there's a lot of redundancy here. If we look at this section here, we've got a cosine, and add, and a multiply. That's the 1 plus cosine divided by 2. And we have to do that for 3 different cases here. And a lot of this is redundant too. Not redundant, but can easily be encapsulated. they used to talk about spaghetti code with go-tos. This is truly spaghetti code, if you ask me. So um, we can introduce the concept of super units. These are encapsulated and reusable code blocks. So I have three super units here. I have fine sliders. So this little block is going to do all of the finding of the sliders, which back here were these three components in the start function, uh, finding the slider, getting its component, finding the other slider and getting its component. And so all of this is encapsulated into the fine sliders. The other one we have is the cosines. So all of this stuff down here that handles all of these cosines is encapsulated into this super unit. And the combined colors has the sliders and the red value. All of this is updated here. And so the flow is pretty simple. In the start, we move to the fine sliders, we get the component, and we set the material. And in the update, we do all the cosines, we combine the colors, and we pass that to the materials get color. And here's one get variable that feeds that material to the set material here, to the set color here, and to the cosines material here. The sliders are all connected to their appropriate input of combined colors, and the red, green, and blue cosines are assigned to their particular values, the output being the color. It also does the set of the UIs. So that's a much more compact view of this, much easier to see what's going on. Here's the fine slider unit, and it has inputs and outputs, and it has flow that goes through find the red slider, get its component, find the green slider, get its component, find the blue slider, get its component, and its output is the red, green, and blue sliders that are those components that I got from each of these. So here's that cosine unit. This encapsulates a lot of the business of modifying all those things. Again, we have input and output. We're getting a variable, the color speed, that's that vector. And we're getting the X, Y, and Z components of that vector, as well as the time. And we're multiplying each of those X, Y, and Z components by the time, which we're then passing to the cosine unit. The X we're passing to the X cosine unit, the Y to the Y cosine unit, and the Z to the Z cosine unit. These are super units as well, the cosine. That was that repeated stuff that does the 1 plus cosine all divided by 2. So with the input and output, we have to define what is coming into a unit, into a super unit, and as well as what's going out. Here's the input We have an enter. This is the flow, the green arrow here uh, um, for my cosines. For my cosines, the flow here is the enter. That's the green arrow. You can hide that label, uh, 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 which makes it then just kind of a green start. And then we have a value input. Those are control inputs. And we have a value input material that's going to come in here. We have to assign it a type. And we have an optional default value if it doesn't happen to be wired up. Um, the so the enter and the flow arrow and material with its appropriate type. And notice down here, it now kind of describes what the outputs of my input module are, is the continued flow and the material. The output has the key exit. So the control is exit. This makes an arrow for the flow to go out. You can hide that label as well. And I'm also outputting the red color, the green, or the red cosine, the green cosine, and the blue cosine. All of these are floats. The labels are not hidden. And here's what the input, what the output's input will be for the next module down line. So that's this module. There's the input to the next module. Here's the input and the flow traversing along here. Now, I have the cosine superunit. This is what does the 1 plus cosine all divided by 2. And this cosine, we're reusing now a superunit. These are all the same, but they, of course, get different inputs from different components here. But they all do the same thing, calculate 1 plus cosine as stuff divided by 2. So it has input, the speed that we want the cosine to operate at. We have a mathf cosine that takes that speed, and I guess you'd call it the frequency. We have flow going across here to the output. But the output of the cosine gets 1 added to it, and then it multiplied by 0.5, and then that value goes to the output, which we then pass on to the red cosine, green cosine, and blue cosine of our superunit cosines that goes on to some other superunit. I'll let you look at the combined colors yourself. So the color version here that's the color cube scripted, sorry. Color bold. Overview. Incidentally, it's Option or Alt and left mouse to pan around in here. You can zoom in on any component, and you can always press the overview to make it go big. And in full screen, we have the flow graph inspector and the overview right there. So again, running this, we see the colors changing this one at a rate of 1, this one at a rate of 2, and this one at a rate of 3, combining to make the colors on my different material. And you can see the flow going forward here. So pretty cool. The cosines, we did this. So there's tons more that you can do with this. And of course, there are tutorials. I found one in CG Cookie that's a quick start guide, and they have a video introduction to visual scripting part 2. Unity has some Bolt tutorials that are archived. And there are samples from the asset store. There's the Bolt Kit third person. This is a little bit glitchy. I'll talk about that in a second, but there's also Bolt Kit first person, Bolt Kit platformer, Bolt Kit top down, and Bolt Kit point and click. I haven't tried any of those, but they look fairly straightforward. And these are game setups that don't use any scripting at all. They're all done with Bolt. I did find that in loading the Bolt Kit third person, it was important that you first load and install Bolt from the asset store, making sure to configure it, choosing human versus programmer and so forth, and then load the Bolt Kit from the asset store. The GUI scene seems to be terminally broken, so start your play in level 01. And the kill floor seems to be broken. Kill floor is something that when you fall off the platform, you restart the level. But I found a fix for that was to increase the height of the capsule collider on the player. It's currently at 2 and it doesn't seem to trigger. You have to make it bigger than the character controller. I found 2.5 worked. And just to show you what that looks like here, somewhere here, here's the level 0. And let's go into full screen. And this is just a silly little game, but it's all done in Bolt. I added I'm not good at jumping, so I added a cheat here so that I can pick up the key, get through the door, pick up the gun, which I can then shoot the patrolling robot with, and make it to the final portal, which of course just puts me back at the beginning of the game again. So, and this is all done with flow graphs and state machines. So, or state machines. So have a look at it and have fun with that. And I'm going to stop the sharing now, and I'm going to end the video. Hope this is helpful. Thanks. Bye.